Qué raro, yo soy el único participante. Hello, good morning, guys. I don't see that anybody has connected yet. Oh, well, thank you. Hello, how are you doing today? Doing good?
Yeah.
Yeah, that's great. So do you already know when you are going to get started having your labs, in the shop?
Next week. Are you in the lab or is it somebody else?
No. I'm not in the lab right now. I am in my house.
No, I mean next week.
I'm going to be in the shop today because I have another group in the afternoon and they are going to get started already. So everything that we are doing here today is going to be part of your lab the second time you go to the shop. So let's wait for the other guys to join in. Hey, good morning, guys. As I said before, so let's get started, So today, we are going to be getting into rectification. One of the most important aspects of the stuff that we are going to be doing in the shop will be you're familiarized with our diodes, you know, and being able to install diodes on a breadboard in order to rectify AC into DC. That's very important because you will be using rectification, you will be using rectifiers even in level 3, even more than in level 2. So you are going to be doing like single phase rectifier, 3-phase rectifiers, and also rectifiers are being used for both DC drive and AC drive. And nowadays, AC drive is pretty much the brain in industry. Okay, so what I want to do first is that I want to, okay, I'm going to show you some circuits that I have on FileStat, and I am going to be posting those circuits on Iconestoga, and it's just a link that you can go to and you can play with those circuits. So last week, what we started to do, and we are going to review that first, last week we started with the halfway rectifier, okay? So we'll go back to that. Give me one sec here, and then okay, so let's get into that one. So here we have a halfway rectifier, okay? So now, when we are going to do the calculation for a halfway rectifier, so let me do something super quickly. I'm gonna be posting this URL. I'm gonna be exporting this as a link, as a small link, and I'm gonna put it on Iconestoga so you can have access to it right away. And that way I make sure that I don't forget doing that later on. So, and it's gonna be under rectification anyways. Okay. I'm gonna call it rectification simulations, as you can see there. And then it's just gonna be a link. So if you want, you can follow through. So the link has been created now. Okay, and now if you want, you can follow through while we go through this lesson. So I'm just gonna open it on my tablet so you can so we can have the ability to do the calculations at the same time. Okay, so you can see it right there. So at first, here we have our power source, which is AC, and then we have our diode. As you can see here, our diode is connected, forward biased. And then we have our load, which in this case is only a 100-ohm resistor. Right here, you can notice that we have the oscilloscope, and the oscilloscope, it's just displaying that we don't have any voltage. We don't have any potential difference between or through across the points, the attachment points of the 100-ohm resistor. Okay, so let's close this switch. And when we close the switch, we start to see that we have our oscilloscope. I'm gonna make it a little bit bigger, okay? And in the oscilloscope, we have only half the wave. I just wanna remind you, because I know we covered this last week, but I just wanted to pretty much be able to review it before we move forward. Like if I wanna be able to calculate this voltage, Okay, so just 1 second here. So I'm going to stop the simulation. So if I want to be able to calculate this voltage, then we are going to have to use our applied voltage from the power source. So we are going to have that the E average, remember please, and that's a very important word, the word average means the rectified DC voltage, okay? So that's gonna be equal to our E RMS times 0.45. Okay, so that's the standard. So in this instance, we are going to have like the reason why here you see that we have 13 point whatever voltage is just because this is displaying the peak voltage. So don't pay attention at this point in time. Don't pay attention to this value here. I'll just delete it. Okay. So the thing that we are interested upon is to know our DC voltage. So when we do our calculation, then we are going to have that the applied voltage that I set out for this was 10 volts times our 0.45. So with the halfway rectifier, we are going to have output DC voltage, which is going to be equal to how much? 4.5 volts. And this 4.5 volts is a DC voltage. The reason why this is DC, despite the fact that you can see that we have a minimum value, which in this case is 0. And even when we have this peak value here that you saw before, it was 13 pretty much. Even when we have the peak value, the thing is that because this wave never reverses its direction, because of that, this is considered DC, okay? Now, this is not pure DC. It is what is called pulsating DC, okay? So this is something important to keep in mind. Pulsating DC. Now, the average value, this is called average. I'm just reminding you this from last week because in the case of the in the case of any of these rectified voltages, this voltage rises to a max value, to a peak value. So we can call this max. And actually on the oscilloscope, you are not going to find the word peak. Okay, on the oscilloscope itself, you are going to find the word max. So peak and max, it's the same thing. So what does it mean? E peak, E max is the same value. Okay, so please keep that in mind. And this max word is the one that you are going to find on the oscilloscope. Okay, so the reason why, as I was saying, this is called an average value is because this is going to go from 0 to a max value over time. As you can see on the horizontal plane, it's going to fall back to 0. And once it goes back to 0, then it's going to go over time again to a max peak value, and then it's going to collapse back to 0. And it will continue in this pattern at this frequency at 40 hertz per second, okay? Because of this, we don't get, I mean, like we got a rectifier that is not like a very, very good rectifier, okay? However, if we only needed like a small output voltage, then it would be fine to be using this. Now, I wanna show you something else also that you are gonna be able to see on the rectifier. Like if I were to install, okay, so I'm gonna install another component here, just because I want you to see this pretty quickly, because that's something that you are going to do in the shop as well.
Sir, I gotta leave. I gotta leave your class right now. I gotta make it to the college for my one of my labs.
Yeah.
So if you could just post this online after, that'd be great.
Okay, yeah. So the only thing that I can do, like I can try to post, you know, the unedited, because I don't really have much time to edit any of this.
Yeah, no, that's okay.
Yeah. Okay, perfect.
Okay, thanks a lot.
Hey, you're most welcome.
Take care.
Okay, so let's keep moving, guys. So in this instance, I'm gonna be running the simulation once more. And I just want you please to pay attention to what's happening. Like right now, you would say, well, nothing happens, right? I'm gonna erase this here. And so far, you can see that nothing has happened. Okay, so I placed a capacitor, like in this case, a 10 microfarad capacitor right there. So what do you think is missing? Maybe to connect it? So let's do that. Let's connect this capacitor. I'm going to add wires. And capacitors are always connected in parallel, okay? So when I connect my capacitor, it seems that the microfarads are too small. I'm only using 10 microfarads. So I'm gonna change that to something a little bit bigger. Okay, so just give me 1 sec here. Okay, I'm gonna have to use my keyboard for this. Okay, so just 1 second. So what I'm going to do now is that, okay, let's see if this is gonna work. Can you see how the wave has changed when I add it? Because I have this load, which is 100 ohms, and I connected a 100 microfarad capacitor in parallel with the load. And please keep that in mind. The capacitor is always, always, always connected in parallel with the load, because the capacitor behaves like a battery bank. So when our sine wave, okay, so let me do something here. I'm going to delete that line so I can place a switch. Let's place a switch here. So you can see what happened when we open and close the switch. Okay, perfect. So if we open the switch, we go back to having a halfway rectification, okay? Now, if we close this switch, okay, so we got our half wave there. If we close the switch, then you can see how the wave changes. And the reason for this new pattern is because the capacitor is charging, okay? And when the capacitor charges, it's gonna be discharging through the load while you have, okay, this point in time, okay, the capacitor is discharging while you have this point in time. I wanna stop it there. So when you lose your voltage, when you lose your source power, then the capacitor is gonna be kicking in and it's gonna fill in the gap, okay? That's why that you have that at that time when you were supposed to have 0 volts, now the capacitor is kicking in and is filling in the gap. So we don't lose voltage at any point in time. Now, I can modify this signal even more if I decide to change the value of my capacitance. Let's go to the one that we are going to be using mostly in the shop, which is 500 microfarads. And let's see what happens when we do that. Okay, so you may say nothing so far. Well, the switch is open, so let's close the switch and look at what happens now. Okay, so you can see that from the last signal to this signal, there has been a huge improvement. Now we can see this ripple. Please keep in mind that the name for this wave is ripple, and ripple is the amount of AC voltage that we have in a rectification circuit. Any questions so far? So that is our half-wave rectifier, okay? So let's keep moving then. Any questions? Is it kind of making sense? Okay. So let's get now into what is the full wave rectifier. And what I'm going to do in this case, as I said before, before we even go ahead and explain how this works, for the full wave rectifier, in this instance, we are going to see a full wave rectifier with 2 diodes instead of 1, like this one with a power source, and just 1 diode. It is our half-wave rectifier, and we were able to improve the average voltage, okay, and eliminate this gap where we don't have any voltage just by applying a capacitor. Also, we were able to see that if we increased the value of the capacitor, in other words, if we increase the capacitance, then we are going to be able to obtain a smoother average voltage, okay? We are going to have a smoother DC, and we are going to increase the value of the average voltage. So if you don't have any questions, then I'm going to stop sharing the screen, and I'm going to show you where I'm going to post. Okay, so let me show you where I'm going to be posting. And it's going to be the same thing as we did before. So I'm just going to be posting now. Okay, just 1 second here. So this other circuit, where we have like a full wave rectifier. So let me do something here. And then with the full wave rectifier, I'm just going to post it right now online. That way you will have access to this circuit. So let's get back into Conestoga. We are under rectification. Once more, rectification simulations, and we are going to create a new one, a new link. So in this case, this is called a full wave rectifier center tap, 2 diodes, okay? Perfect. Now it's being created. Any questions so far? Hope you are good, guys. So let's get into that circuit then. Someone said that he wasn't seeing anything. Can you, I mean, like I am running like 2 screens and I am being able to see everything, you know, like on idle. I mean, of course, I am broadcasting from idle screen, but that's why I have 2 accounts because that way I can monitor if I am able to see the video that I am broadcasting. So is everyone able to see what we are doing here? So you couldn't see it? So right now, no. Right now, I don't have any. I'm not broadcasting anything, you know, other than my voice.
And honestly, you were on a screen, and all of a sudden that screen froze, and then nothing changed on it. So if you were sharing something, I saw nothing, but I could hear you.
Okay, wow, that's weird, you know, because on my side here, so maybe it was a matter of your computer. With all honesty, are you gonna be able to tell what's the issue there? So I'm just gonna go back to, okay, so I'm going to share my screen once more. Hopefully, you know, when I post a video, because all this is being recorded, even if your screen froze, then you are gonna be able to recapture everything that was being covered in class. So, but that happened to me the other day, actually, with my computer, that everything froze and I couldn't keep going. Okay. So right there, well, I can see on my second screen that everything is there.
It changed to you sharing it, but it's just black.
Oh, okay, it's just black on in your end. So
It says Lynette has started sharing the screen. Double click to enter full screen mode. That's all it says. There's nothing else going on.
So is anybody else having this issue? Or is only, probably you're the only one, Mr. Coates, having this issue.
All right.
So anyways, you know what, like I'm gonna be posting this online, and because I'm gonna be posting this online, so try this. Why don't you try to refresh your browser? Are you using Google Chrome? Oh, I guess you are using the application, right? Okay, so let's get moving. So all this is gonna be posted at the end of the day. So we only have about another like 15 minutes. So now we'll keep going, guys. So in this instance, we have a full wave rectifier. So I want you to notice the following, okay? So in this case, we employ two diodes. And because we are employing 2 diodes with a center tap, okay, this is my center tap. So we have 2 sources of power. In the shop, the way that you are going to see it is that you are going to have a step-down transformer that has 2 windings, okay? That one, you are going to have line 1 and line 2, and the center tap is going to behave as our neutral. So on this side, of course, on the other side of the transformer, you are going to have your primary winding, which is going to be connected to your source voltage, which is 120 volts. While on the output voltage, you are going to have 12 volts on either side. Now, first, let's get into the calculation, and then I'm going to explain to you how this full wave rectifier is working. So it is important, okay, I'm going to make like a statement. So it is important to differentiate between a full wave rectifier is not the same like a bridge rectifier, okay? A full wave rectifier is going to do the same thing that a bridge rectifier does. However, the full wave rectifier uses two diodes, while the bridge rectifier uses 4 diodes. And you may wonder, so what's the difference? The difference is that the full wave rectifier uses a center tap transformer, while the bridge rectifier uses a regular transformer, okay? So what's the catch? Buying, I mean, like if you were going to build a rectifier, it is cheaper to buy diodes than to have a larger transformer. That's the catch. Now, when it comes to the calculation, how do we get the voltage? You know, like in this instance, you can see that we don't have that silence, or you know that we don't have the silent moment, or that moment when we are without any voltage. Here, at any given point in time, we always are going to have like a voltage, a source voltage, and a current flow through the load. So when we do our calculation, we have that the E average is equal to our E RMS times 0.9. Okay, so what I'm going to do is that, okay, I'm just gonna make sure that the voltage, okay, is 14.4, so it's gonna be 10 volts. So my RMS is gonna be my voltage, which is line to neutral voltage. So we don't use the voltage from line 1 to line 2. We only use the voltage from line 1 to neutral or line 2 to neutral in order to determine the average value. Okay, so in this case, we have that we have our 10 volts, and we multiply by 0.9, and that's going to be equal to 9 volts, of course. And again, like if we were going to, like if we want to if we want to have a smoother DC, and we want to be able to eliminate the ripple, remember the word ripple in a rectifier? Ripple equals the AC voltage or the AC current. Let me make it like current. AC voltage, current, present at the load side of a rectifier. Fair enough? That's our ripple voltage. Okay, any questions? So far, we're going to simulate this once more. You know, I'm gonna be running the simulation. So far, as I said, you can see that our voltage never goes down to 0. So we are gonna try something here, though. I'm gonna change this back to 100 ohms. And then we are going to apply a capacitor right here in parallel. Remember that before, to make it look like if we have a smooth wave, we needed a capacitor that was equal to 500 microfarads. So let's see what's going to be the value. Like let's explore if we have a full wave rectifier, what's going to be the value of our capacitor, you know, which value will give us pretty much a good signal. So let's get into 100 microfarad capacitor. Let's add another 0 here. Uh-oh, nothing is happening. Okay, so let's do something here then. It's just that we need to be able to connect it to the attachment points. Okay, so in this case, it's gonna be connected to there. It's gonna be connected to here. And now look at what happens, guys. With just 100 microfarad capacitor, then we are able right away to have an even more smooth signal. If we were going to crank this up a little bit, okay, let's take it a little bit more by this capacitance. Let's take it up to the same 500 microfarads that we were using before for the half-wave rectifier. And now look at what happens. A very smooth, a way more smooth, I should say a smoother signal. Now, the beauty is that when we get to the shop, you'll be able to do all this. That's the beauty of this.
Is a voltage like that able to hold a coil in, for instance?
Oh yeah, yeah. Like the reason why we use a coil, it is because like the coil would be connected in series with your load. And the reason to that is that we are going to be using inductance in order to, the same way that with the capacitor, we are able to make our average voltage more smooth. We're going to be accomplishing the same for the current when we use an inductor. That's why that advanced rectifier use both a capacitor and also an inductor. However, in the shop, I don't get into inductors in this class just because if you are not going to see it in the shop, if you are not going to be able to test it and do an experiment with it, I mean, then there's no point in me getting into all the nuances of doing that. However, you know, because we are not going to be able to measure that current with the oscilloscope anyways. So that's why we don't get into doing that. Did I answer your question? Hello, did I lose you? Okay, so let's keep moving, guys. So the last one that we should be able to see, and I'm going to show you pretty quickly. I'm going to build it in front of you. It is the full wave rectifier. Okay, the full wave rectifier, which is called the bridge rectifier. So I'm going to share my screen once more. I'm going to open any of this. And like in this case, I'm going to open my half-wave rectifier once more. And what I'm going to do is that now we are going to use 4 diodes in order to build a rectifier. So check this, please. Okay, so that's still going to be my load. And then now I'm going to have 4 diodes. So let's do this. we are just gonna duplicate. That's what I'm gonna do. My diodes. Okay. Now, how do we connect these 4 diodes? In the case of these, uh-oh, I am missing my diode somewhere. Okay, that's fine. Let's duplicate another diode. Okay. So in the case of these 4 diodes, we want to be able to have an input voltage. Oh, that's what the, okay, here's one. We want to be able to have an input and an output, okay? So in this instance, my power source is going to be connected. Okay, so we are going to have like an input and an output for each one of them. So usually the easiest way to see it is that we connect the diodes like this, like if they were connected in series. Okay, so right here, we are going to have, let's give me 1 second here so I can flip this over. Okay, perfect. Okay, so right here, we are going to have our positive voltage, while right here, add another wire, we are going to have a negative terminal, okay? Let me see why that's behaving that like that. Duplicate terminals. Okay, perfect, there. Now, our power source, on the other hand here, I'll be placing a power source right on the top. It's going to be connected. Let's see if I can make it a little bit smaller, to idle terminals. So one of the terminals is going to be connected right there, while my second terminal is going to be connected right there. Okay, so now we have a full wave rectifier. Two of my diodes doesn't seem to be working. Let me eliminate this switch. View in a scope. Top scope. Okay, I have an issue with this one. So let's put it back into here. Let me see why these 2 diodes doesn't seem to be working. Add a diode from here. Oh, I know why. I just gotta put it, I just gotta place my diodes in a point where is going to work. For example, this other diode should, okay. Look at what happens then. Okay, as soon as I have all my diodes like in the right place, then we can see that with just one source, without having a center tap, we were able to create full wave rectification. Okay, so, and it is cheaper to use more diodes than to build or than to put more windings in a transformer. When it comes to the calculation, when it comes to determining the value of this rectifier, is going to be the same thing as we did before. It's just going to be that the E average it's equal to the E RMS times 0.9. And what's the difference then? The huge difference between the two is that in this instance, this is using only one source. Okay, so it uses a source that doesn't require a center tap transformer. I said it once more, diodes are cheaper than windings. Okay, and they occupy way less space. Most of the rectifiers that you would ever see in your lifetime will be this arrangement. They will be full bridge rectifiers. Now, if we apply a capacitor to this, and I'm not gonna do this at this point in time because we are running out of time already, then of course, this wave is gonna be way smoother. Actually, in the shop, because we're gonna be using like different, I mean, you will be able to explore this load using 25 watts, 60, 100 watts, and even 660 watts loads. Because you are going to be doing that, you are going to see the effect of the load on a circuit, you know, and you are going to be able to see live how that load affects the signal, you know, like how fast it's going to be discharging your capacitor, those affecting your signal. Any questions about this, guys? So what I'm going to do next is that I'm going to be exporting this link. And again, I'm going to get back into Iconestoga and post it on Iconestoga so you can practice with it. So I'm going to be creating a small link, which is called bridge rectifier. There you go. Any questions? Okay, guys. So if you don't have any questions, then this is it for today. I hope that we're going to be able to meet in the shop and that we'll have a chance to be able to go through all this. So anyways, I wish you the best for this week. And hopefully I will be able to see you soon.